Hi, I'm Dr. Shahriar Hossain. Today, I will describe an initial way of exploring and analyzing data using pandas in Python programming. There is a process called exploratory data analysis, which refers to the initial investigation of data. Now, the phrase the initial investigation is a broad term. The initial investigation can be as simple as looking at properties of features or columns in data, or more complex tasks such as finding outliers, finding patterns, or even groups of data points. Exploratory data analysis, or EDA, is a process, not just one algorithm. The process leads to the generation of a good dataset for statistical and machine learning modeling. Unfortunately, or fortunately, exploratory data analysis is a process where steps are not well defined. For different datasets, EDA may vary dramatically. Today, we will be looking at a tabular dataset named Pecan yield dataset. Please excuse my pronunciation of the word pecan. The pronunciation of the word pecan is probably pecan or pecan. In this video, I will pronounce the word as pecan. Please bear with my pronunciation. Whatever the pronunciation is, by this word, I mean this brown nut with edible kernel similar to walnut. The Pecan data has 5 columns: row ID, water per acre, salinity level, fertilizer per acre, and pecan yield. The data has 56 points. That is, the data has 56 rows. Each row of the data contains information about how much water was applied in a season, what was the average salinity level of the soil of the field in that season, the amount of fertilizer given in that season, and what was the amount of pecan harvested at the end of that season. I'll provide a link in the description section using which you will be able to download this dataset and the code I will write today. I will use Pandas for most of the data analysis in this video. I used Jupyter Lab as the editor. You can use Jupyter Notebook, Google Colab, Pycharm, Spyder, or any text editor of your preference. Just make sure that you have Pandas, Numpy, and MatPlotlib installed with your Python environment. Let us jump into the coding part. I have created this empty notebook file named data analysis. I will import numpy as np. I will also import pandas as pd. We will mostly be exploring pecan.csv, this data file, using pandas library. So now I'll be reading the data frame from pecan.csv. And to do that, we will use pandas. So I have pd, which is pandas reference, and I will use the function read underscore csv. And read underscore csv will read the csv file and put it in a data frame. So the file name is pecan.csv. And although this is a CSV file, which practically means comma separated values, I know that this file has columns separated by tabs. So I will set the delimiter as /t, which is tab. And now Pandas has read the CSV file and displayed me the entire dataset the CSV file contains. I will capture the data frame in a variable named df. Now df contains the data frame read by Pandas. Now we'll check how many rows and columns do we have in pecan.csv by stating the statement df.shape, and it is showing us that the data frame has 56 rows and 5 columns. Now we want to see what columns or what attributes, what features do we have in our data. If we want to see the top part of our data, we can say df.head. So this is a function that the data frame contains. So df.head will return us information about the first few rows, including the header. So here we can see that the data has columns row ID, water per acre, salinity level, fertilizer per acre, and Pecan yield. So the data has 5 columns. This particular column, this is not coming from the data. Pandas data frame has added this part to demonstrate that this is row 0, this is row 1, this is row 2, so on and so forth. So this is not a part of pecan.csv file. Similar to df.head, we can also take a look at the bottom part of the data file. You can say df.tail and we'll be able to see the bottom part. So notice that df.head gave us the top 5 rows of the data, and df.tail is giving us the last 5 rows. And I know that in this file this row ID has 1 2 3 4 5 6 7 8 9 10 up to 56, because there are 56 rows, and this last 5 rows, that is 52, 53, 54, 55, and 56, these rows are displayed here when you are using tail. For any dataset, the head will give you the top 5 rows and tail will give you the bottom 5 rows. Now we can explore more information about this particular data frame. You can say df.describe, and df.describe will give us a lot of information, a lot of statistical information about the columns, about the features we have. It is telling us that the row ID, it has 56 count, means 56 entries, that is 56 rows practically. Water per acre, there are 56 entries. Salinity level, 56 entries, of course, because we have 56 rows. Same goes for fertilizer per pound as well as for pecan yield. Then for every column, that means for every feature, we have the mean. We know that row IDs are starting from 1, and with an increment of 1 it goes up to 56, and the mean of all those numbers would be 28.5. Whatever information we have in water per acre column, the mean or the average is 78.427549. Similarly, the mean for salinity level is provided here. The mean for fertilizer per acre is provided here. The mean for pecan yield is provided here. The standard deviation for every field or every attribute or every feature of the data would be provided here as STD. This mean is what is the smallest number in that particular column. So in row ID, the smallest number is definitely 1, and it is 1. And in the water per acre column, the smallest number is 40. In the salinity level column, the smallest number is 10. In fertilizer per acre, the smallest number is 25. The pecan yield has the smallest number of 310 in that particular column. Then max is this. We already have seen that row ID has the largest number 56. So the largest number in row ID column is 56. For water per acre, this is the largest number. Similarly, for salinity level, this is the largest number, so on and so forth. Let's talk about what this 50% means. This 50% means what is the median of every column. Here for water per acre 77.604481 is the median of that column, so and so forth. Note here that 50% of the numbers in a given column are smaller than the median of that column by the definition of median. What is this 25%? It is actually 25 percentile. It is a number smaller than which you have 25% of the numbers in that column. You have 56 numbers in each column, so you have 56 numbers in the column water per acre as well. 25% of 56 is 14. 25 percentile of water per acre is reported as 59.916263. In the column water per acre, you will find that there are 14 numbers that are smaller than 59.916263. That is, this 25 percentile of the column is computed in such a way that 25% entries of that column are less than this number. Hence, 14 entries in that column will be smaller than 59.916263. Similarly, there are 14 entries in column salinity level that are smaller than 17.193919. Similar statements will go for fertilizer per acre and pecan yield. A 25 percentile of a feature is sometimes called the first quartile. Now, what does this 75% mean? It is just like 25 percentile, except that 75% of the entries of the corresponding column are smaller than 75 percentile. Here, the 75 percentile of water per acre is 95.905961. 75 percentile is computed in such a way that 75% of the numbers in the column water per acre are smaller than this number. That is, in the water per acre column, 42 numbers out of 56 are smaller than 95.905961. A 75 percentile is sometimes called the third quartile. In this row, you have the third quartile for all the columns of the data table. So that is the describe function. The describe function will give us these statistical measures actually for every column. And that is excellent because from these information pieces we will have certain idea about this data set that we are analyzing. We can even check if we have any missing values or null values in our data. We can say df.isNull. So isNull actually provides a matrix of whether there are cells containing null values. So if you take the sum of that matrix, we will actually receive in each column how many null values are there. So in row ID column, there is no null value. For water per acre, there is no null value, so on and so forth. For all the columns we have, there is no null value. So there is no missing data in this given data set. Just like this describe method, we could particularly look at a specific column and we could ask to describe that particular column. We could just mention df and in square brackets we could provide the column name or the attribute name, and we could say describe it, and basically the data would be described here: the count, the mean, standard deviation, the smallest value, and 25th, 50th, and 75th percentile values would be displayed. The numbers we have in this particular column are floating point numbers, float 64 data type. Speaking of data types, we could know more about these data types just by typing df.info. We will receive information about this particular data frame. There are 56 entries, that means 56 rows, and there are 5 columns. And these are the column names, and 0, 1, 2, 3, 4, these are the column indices. The first column row ID, that is integer, and the rest of the columns are floating point numbers. The memory used by this particular data frame is 2.3 kilobyte. Let's say that we want to take a look at if there is any obvious relationship between these columns. There are many different ways to find out relationships or correlation between columns or between attributes. But here we are exploring. So when we are exploring, we probably want to just take a look at things visually. We will create some diagrams to see if we can visually detect any relationship between the columns or pairs of columns. Let's import MatPlotlib, which you are already familiar with from the previous 2 videos in this workshop series. I'm importing that MatPlotlib's pyplot facilities. I will use this PLT, that is this pyplot, to draw a scatter plot, which would be a 2-dimensional scatter plot between, let's say, 2 fields like water per acre and Pecan yield. Water per acre is how much water was given in a season in this pecan field. Pecan yield is how much pecan was produced at the end of that particular season. We have this df, and from df we want to entirely retrieve the column water per acre. And we'll keep this water per acre in the x-axis of our scatter plot. In the y-axis of our scatter plot, we'll be keeping pecan yield. So we are retrieving entirely the column pecan yield. Now, if we execute this line, plt.scatter should draw scatter points in a 2-dimensional plot where water per acre would be in the horizontal axis or in the x-axis, and pecan yield will be in the y-axis, that is the vertical axis. So this is horizontal axis, x-axis, which is water per acre, and this is y-axis, which is pecan yield. Do we see that the more we go to the right side of the figure, that means the more water is given to the field, the more pecan will be produced. So pecan yield is actually highly dependent on water per acre. At least from this data, it seems like when there was more water, there was more pecan yield. That means more pecan was produced. That's a finding. So we are saying that, oh, okay, if someone gives more water in the pecan field, there will be more pecan based on this data. Of course, if someone floods the entire field with water, there might not be a good amount of pecan. But this data is telling us that the more the water, the better the pecan yield would be. So let's check what happens with the salinity level. Salinity level is what is the amount of salt in the soil. To some extent, we know that for some plants, too salty soil might not be good. Let's see what this particular data says. In the x-axis, we have now salinity level, and in y-axis, we have pecan yield. And the more we go to the right side of the plot, the common trend seems we will have lesser and lesser pecan yield. So higher salinity might not be good for pecan yield. At least this data is saying so. The data we have in our hand is saying that the more the salinity level of the soil, the lesser the pecan yield. So pecan yield is negatively related with salinity level. So that is what we found. Now, what does our Pecan dataset tell us about the relationship between fertilizer per acre and pecan yield? I will leave this question as an exercise. Please comment below on what you find about the relationship between these two features. In this video, I have only shown some simple ways to explore data. When you receive tabular data from a client, you can start the exploratory data analysis using my demonstrated approach. However, datasets differ drastically. Familiarity with the functions in Pandas is immensely beneficial for exploratory data analysis. If you go over Pandas documentation, you will find many more functions that you can use to get insights into the data. I am planning to use the Pecan dataset in the future to explain predictive models. Please stay tuned and subscribe to this channel to receive notifications directly from YouTube when we publish any new video. Thank you.